Good afternoon. We're a third quadrant design from the University of British Columbia in Vancouver, Canada. Today, we will be presenting our design for the Urban Single-Family Design Competition, Solace House. The team is led by myself, Zoe Lehong, along with Claire Pobrovic and Alicia Sue, with the support of 3 faculty members, Dr. Susan Nesbitt, Dr. Cheryl Staub-French, and Dr. Adam Reisenek. Headshots of our team leads can also be seen on this slide, whom lead design in our 6 subteams. This slide shows our team roster, comprised of 26 undergraduate students, all studying various disciplines of engineering. Subteam leads are shown in bold. We are lucky to have the sponsorship and support of local companies and organizations, including UBC's Faculty of Applied Science and Civil Engineering, the Engineers and Geoscientists of British Columbia, Integral Group, RJC Engineers, RDH Building Science, and Frankel Architecture. Solace House is located in Vancouver, BC, which is in Climate Zone 4, characterized by mild, temperate conditions. Due to its proximity to mountain ranges in the Pacific Ocean, there are very high levels of precipitation in Vancouver. On average, over the last 25 years, it has rained for approximately 166 days a year, totaling 45 inches of annual rainfall. There is also relatively little sun. According to the National Renewable Energy Laboratory, Vancouver gets less than 3 kilowatt-hours per meter squared of solar radiance per year, much less than most of the United States, and which exempts the home from the Department of Energy's Zero Energy Ready Home PV Ready checklist. Nevertheless, the site is in a beautiful location, located near the water and mountains alike. Directly north-south facing, the lot itself is extremely narrow, with dimensions of about 33 by 121 feet. There are several trees on the perimeter of the site, with one requiring removal for construction. This site is located in Vancouver's Hastings Sunrise neighborhood, a predominantly residential area. The Hastings Sunrise neighborhood has a rich history and diverse population, featuring many parks, community centers, and nearby commercial areas. The average residential occupancy size is 2.7, with the majority of residents between ages 20 to 64. The median annual household income is approximately $86,000 Canadian per year. In 2016, Hastings Sunrise developed a community vision report to identify residents' needs and wants for the future of their neighborhood. Residents identified significant value in the area's distinct single-family homes, scenic nature views, and walkable shopping areas. Core values of the community vision include creating a cleaner, more environmentally sustainable community, building a safer community, maintaining and enhancing single-family neighborhoods, and increasing housing variety by encouraging two-suite homes. Solace House was developed to suit current neighborhood demographics and address the needs and values expressed in the Hastings Sunrise Vision Plan's community goals. The market potential of this home is immense. As Vancouver is one of the least affordable housing markets in the world, this home stands out as a feasible, affordable, community-centered net zero home. By focusing on community vision goals such as increased unit density, community food production, and understated architectural design, Solace House has the opportunity to be readily embraced in Hastings Sunrise. During the construction phase of this home, the owner will reap the benefits of a modular design, reducing construction time and labor costs. Once the house is built, occupants will enjoy a comfortable and beautiful environment sustained by integrated smart home systems that monitor and control thermal comfort. Resilience was a key driving factor in the development of our design. Some main risks due to location and long-term functionality were identified. First, Vancouver is located in a seismically active region and is considered at high risk for a serious event as depicted by the Seismic Hazard Map of BC. This requires careful attention to seismic resilience in the structural design of the home. Second, while contributing to the mitigation of climate change in the design of a net zero building, the team wanted to ensure long-term comfort with the reality of a changing climate. Vancouver is predicted to have longer, hotter summers, causing periods of drought and cooling days increasing from 18 to 43 days a year by 2050, as seen in the table presented. More extreme precipitation events are also predicted, causing increased risk of flooding. Another area of risk is electrical grid connectivity. Ensuring self-sufficiency in the event of a power outage is very important. Additionally, due to Vancouver's high levels of precipitation, damage due to moisture ingress in building envelopes is a very common issue in the area, so a high-performing envelope is vital. Finally, given the high cost of housing in Vancouver, it was desired that we address a risk of income crisis in the event of a lost job. To respond to the needs of the community, the principles of the solar decathlon, and a desire for resilience, the following design concept was conceived: to create a dwelling that addresses all levels of sustainability, low embodied and operational emissions, as well as long-term resilience. The design will be approached with a passive systems-first mentality and a utilizing transdisciplinary communication to ensure seamless integration of active systems. Accordingly, Solis House has successfully incorporated some key components: on-site renewable energy, modularity, a high-performance envelope and fenestration system, the use of local, low-carbon intensive materials, the use of passive principles in building form and envelope design, overheating mitigation measures, a mass timber structure, the presence of site-related alternative income sources through food production in a rental suite, and rainwater collection. We will commence with an explanation of the architectural design of the structure. The main architectural design goals of Solis House were to highlight local, natural resources to establish uniqueness while maintaining the theme of its neighborhood. The home creates a space that complements its surroundings on the outside and feels comforting and breathable on the inside, despite the narrow lot. It even features a 690 square foot rentable studio that increases density and provides a secondary income source for the homeowner. The design was primarily guided by passive principles to reduce as much energy load as possible up front and support the active systems that would be present. These principles could be incorporated into the architectural design through building form, in simplifying the shape to reduce envelope surface area and increasing the roof area available for solar energy generation. At a total of 292 square feet, internal spaces were designed to enhance natural ventilation and lighting, and rooms were placed based on heat requirements. The mechanical room was placed on the cooler north side of the house, and appliance-heavy areas such as kitchens and bathrooms were positioned close to the mechanical room and were stacked to reduce piping. Bedrooms are in central locations, away from the road and high-traffic areas. Thermal mass was also considered in open-plan living spaces, through the use of concrete flooring that receives sunlight during the day and can release heat in the cooler evening hours. Operable window size, type, and placement were carefully selected to enable effective natural ventilation, ensuring adequate airflow within Solis House. In the summer, a nightly flush allows for passive cooling and enhanced air quality. Double-height spaces maximize stack effect. And in the small unit, a clerestory window allows the entrance of natural light, while the absorption of heat by the roof enhances convective airflow throughout the open-plan space. The interior is regularly exposed to natural light, creating a comfortable space for its residents. Furthermore, the warmer and light colors chosen for the walls and floors diffuses sunlight throughout the home, further accentuating the livability. Here you can see natural lighting at midday during the summer solstice. Many parts of Solis House are sourced to ensure low embodied carbon and the use of natural materials, from the use of local wood in the structure to the countertops, which are made from recycled oyster shells. Solis House's style also integrates cohesively into its neighborhood. Despite its modern look, it honors the nature and history of the surroundings, with its locally curated materials, as well as being designed similarly to the increasingly popular West Coast modern home.
Now we will move on to the landscape. Our landscape design was based on the principle of maximizing the utility of our land available. We've included a vertical garden built into the house, as well as on-site food production to the south. Both systems utilize an irrigation system supplied by our rainwater harvesting system and could be expanded with increased rainfall. We've included a significant area with locally supplied core gravel permeable pavement, which features a recycled plastic permeable base infilled with gravel. This allows for the site to naturally drain any excess water, which our harvesting system does not collect. To help with the drainage, we have also graded the site at a 2% slope away from the main structure. The material from the removed tree would be suitable for use within the house for furnishings like furniture. The remaining trees are unobtrusive and provide shading on the lot. Now we will go over the structure of the house. Shown above are the floor-to-wall and wall-to-roof details for the structural system. Since Vancouver is located in an active seismic zone, we have selected building materials to mitigate the effects of an earthquake. Cross-laminated timber, or CLT, provides improved performance because of its strength, flexibility, ductile connections, and lightweightedness. The bubble deck slab-on-grade technology reduces earthquake loads when seismic loading governs the design, which is especially applicable for the location of Solis House. The use of bubble deck decreases the amount of concrete used while maintaining the performance of a typical slab. The system consists of a grid of high-density polypropylene spheres laid on precast panels and reinforced with steel bars. These prefabricated panels are transported to site where they are connected by lap reinforcing bars and concrete is poured on top to finish. This results in a reduction in concrete by 30 to 40% and a decrease in CO2 emissions by up to 50%. Additionally, the tie-downs at each corner of the house will assist in resisting lateral seismic loads in the event of an earthquake. Now we will go over the construction sequence. Solis House will be constructed using modular construction techniques with prefabricated insulation units and CLT panels for the enclosure. Building with prefabricated panels has been proven to provide stronger structural characteristics, higher air tightness, better thermal resistance, faster framing time, and a reduction in construction waste. Panels are also customizable, can be pre-cut, and are factory controlled for consistent quality. As shown, the building is constructed story by story, with the ground floor's exterior walls placed first, followed by the ground floor interior walls. The process is repeated for subsequent levels.
To complement our wood structural systems, our building envelope showcases carbon sequestering and hyperlocal products sourced and produced right here in the Lower Mainland. Our envelope includes FP Innovations wood fiber insulation boards, a dry processed, non-structural wood fiber product that provides excellent thermal and acoustic performance. These boards are sandwiched between CLT panels from Structurecraft and Pine Cladding. Both products can be sourced and produced in and around Metro Vancouver. By volume, 97.8% of our exterior wall sections are made out of carbon sequestering hyperlocal wood products, sourced and manufactured within less than a 25-mile radius from our site. Showcasing innovative local products and reducing the carbon costs of our envelope, we also had to deal with Vancouver's cold and wet climate. Vancouver experiences an average of 165 days of rain a year, and over the last 10 years averaged a morning relative humidity of 86%. As a baseline, we use Passive House Canada standards to design our envelope. The table on this slide shows the Passive House Canada benchmarks we used and the calculated R values we were able to achieve for our exterior envelope sections. Figures 1 and 2 shown here model our wall section under 100% relative humidity and negative 18 degrees Celsius conditions. These conditions were the least favorable daily averages for a period of 10 years. According to these models, condensation and wetting are considered very unlikely in this construction. Figure 3 shows the Thur model of our typical window, a triple glazed fiberglass frame window with a low E coating. As you can see, such a window yields a nice gradual temperature gradient. This gradient is desirable as it prevents sudden freezing, condensation, and confirms that there are no thermal bridges through this window. Additional attention was paid to the acoustic properties for our building envelope as well as our interior walls. The standard of privacy for sound transmitted through the air is 50 STC and 50 IIC for sound transmitted through impact, which is especially relevant for floor assemblies. Assemblies were referenced to STP and ICC values found in studies commissioned by the Canadian government. For the roof, exterior walls, and interior walls, our chosen assemblies met the standard of privacy requirements. To increase our floor's ICC, we chose to use 12 millimeters, or about a half-inch of acoustic cork floor underlayment to adequately dampen impact noise. Acoustic comfort in the home is also improved by dampening external environmental noise with honeycomb acoustic foam attenuators and street-facing openings. These attenuators reduce street noise by about 30 decibels while maintaining airflow requirements necessary for natural ventilation.
Moving on to mechanical systems. The driving principles for the mechanical design were occupant comfort, energy use and simplicity, and 100% electrification of systems. Heating and cooling systems were designed to closely conform to ideal human temperature profiles. Mechanical systems were designed to minimize energy use without over-engineering, and this was done by maximizing passive methods and minimizing active mechanical components. A closed-loop geo-exchange system is at the heart of the home's heating and cooling. A comprehensive heat loss calculation informed current and future peak heating and cooling loads. A geo-exchange system consisting of a 6.75 kilowatt ground source heat pump coupled to a single 120-meter vertical borehole was chosen. The system was sized for future heat rejection capacity based on expected future peak cooling loads. On the supply side, the ground source heat pump extracts and rejects heat to a hydronic radiant heating and cooling system. This system is zoned and each zone is thermostatically controlled. During operation, a central controller receives temperature and humidity data from the thermostats and determines a set point temperature for the system. In cooling mode, floor surface temperatures may not exceed the dew point temperature of air in the space to mitigate condensation on surfaces. And in heating mode, floor surface temperatures may not exceed 29 degrees C to mitigate excessively hot surfaces. A radiant system was chosen over forced air for a number of reasons. Radiant heating profiles closely align with ideal temperature profiles. People are most comfortable when their feet are slightly warmer than their cores, and their heads are slightly cooler. Hydronic heating and cooling requires smaller operating temperature ranges, which reduces loads and allows the heat pump to operate at higher efficiencies. Radiant cooling also opens up the possibility of passive cooling, where system water can exchange heat with the ground loop of the ground source heat pump while the heat pump itself is not in operation. Additionally, decoupling the heating and cooling from ventilation leads to a more efficient ventilation system. While the radiant system can meet both heating and cooling demands, a changeover mixed-mode ventilation system is projected to provide adequate cooling for the house during summers. This is, however, expected to change as the climate changes. In a changeover system, natural ventilation is used in milder weather and mechanical ventilation in more extreme weather. The mechanical ventilation system consists of an energy recovery ventilator, or ERV, that operates continuously, providing approximately 18 degrees C filtered fresh air by pre-cooling and preheating supply air. Ventilation is demand controlled and based on occupancy, operation, and air quality. The ERV can operate in boost mode to meet additional exhaust demands of the kitchen and bathroom operation, and can promote air changes in response to indoor air quality sensors. The ERV can operate in reduced ventilation mode when the house is unoccupied. For domestic hot water, a hybrid hot water heater was chosen. The heater operates as an air source heat pump to meet standard demand, and an integrated electrical resistive element provides additional heating for increased demand. In heat pump mode, both heat is extracted and cool air is rejected into the mechanical room, providing free cooling. Cooling the surroundings has beneficial effects as it helps to offset the heat generated by the equipment in the mechanical room. A simple copper heat exchanger allows for drain water heat recovery, which captures waste heat from showers and dishwashers. This can increase the temperature of the incoming cold water by about 15 degrees, helping to reduce domestic hot water operating loads. Plumbing was designed to minimize the usage of water, power, and materials by selecting low-flow fixtures and Energy Star appliances. Bathrooms, kitchens, laundry facilities, and the mechanical room are all located adjacent to one another to minimize pipe lengths and associated heat losses. And bathroom groups are also wet vented to reduce the length of vent piping. In a world affected by climate change, water quality and availability can quickly deteriorate. To improve resiliency and off-grid capabilities, a rainwater harvesting system is implemented. Rainwater is directed from the roof to a 10,000-liter tank capable of supplying non-potable needs, that is, toilets, washers and dryers, and irrigation for the vertical garden. The tank is sized for a month's supply without rain. There is additional dedicated space for a future filtration system, such as a UVA or UVC sterilization chamber, to allow for potable system retrofits. Tank overflow is directed into city stormwater drainage, and an additional 750-liter tank collects garage roof runoff for outdoor irrigation. This non-potable system can also be supplied directly by city cold water if needed.
Now we're going to talk about electrical systems. For lighting, because we had more natural daylighting available to us, we were able to meet a lighting load target of 1.57 watts per square meter in the house. Lighting levels in our house without natural daylighting averaged to about 80 to 100 lux per room. To reduce lighting load, we implemented a lighting control system, which is shown here, to include more efficient energy use through daylight harvesting and vacancy sensing in various areas of the room. The lighting designed for each unit is a wireless system solely controlled over Crestron Infinite X network, which allows each fixture to be controlled using a low voltage system. This also allows each lighting zone in the house to be controlled via smartphone applications as well as manual switches. And this also allows dimming of each lighting zone, which gives the occupants the flexibility and the power to customize the mood desired for each room. So for power, in addition to the standard power layout shown on our slide here, we've also implemented Legrand Smart plug load modules, which are also shown in our slide here. These are used to manage and control various loads through a plug load management system, which is really helpful to us because it'll effectively shave peak loads and reduce the stress placed on our electrical system. Next, moving on to energy performance. By using REM rate, we were able to estimate our energy demand to be around 8,000 kilowatt hours per year, and by using NERL REOP, we estimated our utility bill in Vancouver to be around $240 a year. This is a significant reduction compared to an average Vancouver home's annual electricity bill of $1,250. To meet the net zero requirements of the competition, we wanted to make sure that we hit a HER score below 0 with our PV system. Therefore, Solis House has a HER score of 34 without PV, and with PV, a HER score of -11. Using the energy demand from REM rate, we sized our solar system to generate 100% of our per annum energy use. Because of Vancouver's temperate climate, generating enough solar power all year round is not feasible, so we went with a grid-tied system to allow us to sell power in the summer and buy back power in the winter. Our system's electric components then had to meet BC Hydro requirements for net metering. Because Solus House used electricity for all its appliances and heating needs, making sure the home was resilient to grid failures was a key design consideration in our energy systems. We used PV Watt and REOP to estimate the performance of our system and how large our batteries needed to be to meet our resiliency targets. Our batteries also supported the resiliency of the local power grid by smoothing out our peak demand loads and lowering our power bill.
Solus House was designed in the context of Vancouver's housing affordability crisis. This house provides a feasible opportunity to live in a net zero energy home that is competitively priced within the current market. The cost to build Solus House was estimated using RS means to be $389,012.47. Based on Hastings Sunrise's average land costs, our lot's market value would be $1.35 million, bringing the total list price of this house to just over 1.7 million Canadian dollars, well below the average price of a two-story home in Vancouver. Assuming a double median income Vancouver family puts down 20% upon purchase, takes on a standard 25-year mortgage, and rents out the unit at market rate for passive income, their debt-to-income ratio would be about 48%. The average housing-related debt-to-income ratio in Vancouver is 208%, making Solus House a far more affordable option for the average Vancouver family.
Now we will move on to embodied carbon. The scope of the LCA includes the building's major structural components, excluding finishes and furniture, since their contributions are not significant compared to major building assemblies and they can be easily changed over the building's lifetime. The house was designed to be resilient and durable over a lifetime of 100 years. Due to high levels of thermal insulation and high-performing envelope components, Solus House sees a significant majority of its embodied carbon contributions coming from the upfront materials stage. Relative to other life cycle stages, this is a large contribution, and the benefits can be seen in the low operational emissions due to the high efficiency of the house. Solus's on-site energy generation and high-performing envelope allow the residents to consume less than 50% grid-provided electricity than a typical Canadian single-family home. Sensitivity analysis showed a significant improvement in embodied carbon by lowering this consumption load. Solus House improved its overall embodied carbon from 671 tons CO2e to 169 CO2e, just by reducing the grid power consumption of the house by effective envelope design, on-site power generation, and passive space conditioning strategies.
Solus House was designed to incorporate innovative and efficient solutions that are tangible, feasible, and scalable in today's high-performance building industry. Materials were selected that significantly reduced material wasted and embodied carbon whilst increasing energy performance and reusable materials. Recycled plastic honeycombs used in pathways and carport foundations are a locally manufactured product which control runoff and support groundwater infiltration. Bubble deck technology for the slab-on-grade foundation is completely recyclable and reduces concrete whilst maintaining the performance of a typical slab. The kitchen features composite countertops which repurpose a local waste stream of oyster shells as aggregate and perform equivalently to granite countertops. Cross-laminated timber supports structural loads and seismic risks while simultaneously reducing carbon emissions. Wood fiber insulation from FP Innovations provides superior thermal performance and reuses waste streams from one of BC's largest industries. The house is designed to be self-sufficient, featuring on-site solar generation, allowing Solus House to meet net zero energy status. Additionally, on-site rainwater harvesting exceeds water consumption needs. This effectively decreases operation costs for occupants and increases the resilience of their home. The indoor greenhouse is vertically configured to significantly reduce the amount of water required to grow plants. Lastly, on-site food production provides residents independence, food security, and an opportunity for a partnership with a local company to create a community farm on Solus House's site. All of these elements contribute to Solus House's quiet and unique presence within its Vancouver neighborhood, a small yet open, natural, and breathable living space that accommodates up to 5 residents. Thank you very much, and we're happy to field any questions.